Okay, so in this one we're going to take a look at a problem that I remember from back when I was doing tutoring. I don't remember all of the numbers, but I think I've got it pretty well reconstructed. I remember calling this one in my mind bad day for Olaf. The way I've got this written up, a young man named Olaf is playing full contact sports ball. He has a mass of 55 kilograms and catches the ball. Sadly, after catching the ball, he gets tackled by Sergio, a 110 kilogram first base goalie back. Assume that Olaf is standing still when he catches the ball. So, if we take a look at this, we've got Olaf here. Ignore the poorly drawn arm there. And he has caught a ball. There's a sport that uses a pineapple as a ball, right? And he is being tackled by Sergio. Sergio has an initial velocity. The velocity of Sergio is going to be equal to 5 meters per second. Sergio also has a mass of 110 kilograms. In this case, I've set it up where Sergio is moving to the right. He's going to tackle our dear friend Olaf. Olaf has a mass of Olaf. Let's put in, actually mark these. Mass of Sergio. Mass of Olaf, which is 55 kilograms. Did I say 55 or 50? 55. Okay? And he starts off, he catches the ball at rest. Velocity of Olaf is 0 meters per second. Okay? Well, in this case, we have a situation where Sergio tackles Olaf. And the way that I've got this set up, unfortunately that stuck to that, but that's okay. Use your imagination. I set up that Sergio grabs Olaf and that they stick together. So basically we're dealing with an inelastic collision. And that is a circumstance in which the two objects end up sticking together. Kinetic energy is never conserved in that case. Ignoring the mass of the ball, or in this case, the way I've drawn it, the pineapple, and ignoring any friction from shoes or anything like that, how fast is the combination of Sergio and Olaf going immediately after impact? So basically what I've set up here is we're ignoring any significant external forces that might be there. You can imagine that Sergio's kind of gone off the ground, he's doing a diving tackle, and Olaf does not have like cleats or anything. He'll be picked up pretty easily on that, which is most likely the case. So, with no external, no significant external forces, that means that our momentum is conserved. Okay, well conserved, as I have said many times, means what you start with, you end with. Okay, well let's take a look at what we've got. What we start with is, well, we've got some momentum here in Sergio. It is going to be equal to velocity of Sergio times the mass of Sergio, which is our momentum. And I'm going to add that to, he's not the only one with momentum. We've got Olaf, who has the velocity of Olaf times the mass of Olaf. Okay, we're going to set that equal to what we have at the end, which is going to be, we know that they stick together, so we have some object, which is the mass of Sergio plus the mass of Olaf, ignoring the mass of the ball, times the velocity that Sergio-Olaf mass is moving at. And this is what we want to find out. Okay? So if I start plugging in my values, we have this from before. We've got Sergio is moving at 5 meters per second. His mass was 110 kilograms. Plus value of Olaf's velocity, which was 0 meters per second, because he starts off not moving, times his mass, which is 55 kilograms, which doesn't matter that much because it's multiplied by 0, but even still, equals their combined mass, which is going to be 110 plus 55 kilograms, where the kilograms is on both of those, times our final velocity. Okay, well, I've got an equation, and the only thing I don't know is my final velocity, so I'm going to divide by 110 plus 55 kilograms, so I can get my final velocity by itself. And I will find that with this guy equal to 0, we've got a situation where 5 times 110, we're going to have 550 kilogram meter per second, also known as Newton seconds. I'm not as fond of that. I usually deal with the kilogram meter per second myself. I divided by, right here, oops, I should actually mark that. This whole side's going to be divided by 110 plus 55 kilograms. I apologize. If I divide it on this side, I need to do the same thing over here. I got distracted. So we're left with 110 plus 55 kilograms, and that is going to be equal to our final velocity. When we do that, that's 165, so we've got 550 kilogram meter per second divided by 165 kilograms. We'll see that the kilograms are going to cancel out. That leaves us with meters per second, which is good because we're looking for a velocity. We find that our final velocity for the combined mass is something like 3.3 meters per second. I believe it's 1/3 meters per second, basically, because it's 3 repeating. Okay? But we have found the bad day for Olaf. Again, we went through and we set up and had a situation where we draw out our situation. We check to see if there are any significant external forces. If there aren't, then we can apply conservation of momentum. And conservation, as I have said many times, is what you start with, you end with. So you just go through and you find all the little things you start off with. In this case, we're dealing with momentum, so we find the momentum of this guy, the momentum of this guy, and if we had 1,000 other items in there, then we would just do the momentum of each of them. We'd add them all up to find out what we start with, and then we set that equal to whatever we end with. And we go through and try and fill in numbers. Hopefully you've got enough information to fill in enough that we can finally solve for whatever it is we're looking for. In this case, we could. So we just fill in our numbers and set what we start with equal to what we end with and solve for what we want.